Types of gloves that we use. What are the types of gloves? Latex and
Nitrile.
nitrile. Latex is more natural products, and nitrile is a chemical, it's a synthetic material. We use those to protect our hand. For some chemical, it may be not enough. We have to wear another layer of gloves. You have to wear, what do you call it? The chemical gloves. Those are thicker gloves which we wear. We don't throw them away. They are used by a certain times and before they are replaced. We might have to wear an apron, right? So when we are working on a hood, we reduce the chances of our gown to get contaminated. Apron may be replaced easily then. So before we handle a chemical, what do we need to know? MSDS, right? And that will tell us about PPE, right? That will tell us about, very importantly, what do we do in case of a spill? Some of the chemicals, we just don't attempt to clean it. We just clean the place, right? In some other cases, we may be able to use some neutralizing agent. For some chemicals, we may just wipe it and that's enough, right? For everything is dictated or defined in MSDS, right? So gowning is two-way. One is to reduce the dust particles, oil, whatever we can contribute to the cleaning. The other side, it's the requirement of PPE, personal protective equipment. Make sense? So it's to your advantage to follow these rules. Right? So shortcuts are not allowed because those chemicals are, some of them are really bad. For example, BHF, which is a very common etching agent for, what do we use BHF for? Silicon dioxide, right? It's a very common etchant for silicon dioxide. We use it a lot because every step before every step we oxidize the deposit. BHF is hydrofluoric acid. If it gets on the skin, we don't feel it. We feel when fluoride gets to the bone and reacts with calcium. It's very painful. That's one of my instructors to say excruciating pain is caused by BHF. So we have to be very careful with these things. And there's certain things that need to be done for different chemicals, not just in spill. If we get exposed on skin, maybe we breathe it, maybe we I don't know, inhale it, or we get it in our mouth or get in our eyes. So there are certain things that need to be done. In case of BHF, what is the first thing that we do?
Wash, I guess.
I'm worried about you guys. If you are still guessing before you go to clean room, what needs to be done?
In the MSDS.
There's no guesses. We don't do guesses then. This is not good. Next week you guys are going into the clean room, right? If you get BHF on your skin, what do we do? It's not a guessing game. I won't let you go inside the clean room. If you guys don't know what needs to be done, get BHF on the skin. So all the chemicals, we'll give it a try again on Thursday.
You find a solvent for that in the MSD.
You need to, no, that's right now, from my point of view, are ready to go inside the clean room. And this is covered in the training, in the safety training. You gotta look at all these things, and you have to know. Thursday, I'll try it again to figure out if you guys know what needs to be done for these basic chemicals. You gotta find out, right?
They actually have something for VHF exposure that
There
you
is a
put
cream
on, right?
called something glutonate or something. There is a cream that needs to be put on.
But first you have to wash for it.
We don't guess, we wash it. So we have to know if we are going to wash it or not. If we keep on continue washing it, or after washing we have to apply some cream. So you have to know all these things. So that's something Thursday I'll have to assess it again. I need to talk to the staff and NanoFab because you guys need to know all these things. Some basic, these are simple chemicals that we'll be using for cleaning. Whatever we have discussed on cleaning, whatever chemical goes in there, you have to know. You have to know the MSDS, PPE, what happens if it's a spill, what happens if there's an exposure of that chemical. Right? You know all the chemicals that we use for cleaning. At least those you have to know to get started. So we have done some modifications in those simple RCA methods. One is called diluted standard clean one. So we dilute it a lot. We add lots of water in this. It improves the roughness. We don't want surface to roughen up, so that reduces the roughness effect. And we use less amount of chemicals. So if you have NH4OH, you gotta know what do you do for ammonium oxide, ammonium hydroxide. Right? It's ammonium hydroxide. You have to know what do we do, how do we deal with hydrogen peroxide, all those things. There are some sort of chemicals that can accumulate on the surface of silicon. We call them surfactants. They sort of have affinity to accumulate on the surface, but they are not good. We might want them during the cleaning process, but after that we have to react them and remove them. So after every cleaning step we do, of course we need to inspect it, and if we have to remove the whole oxide, we do VHF it. If it is, we want to retain oxide, we just do an HF dip, just to get rid of this very thin layer of oxide from the top. And we seldom use HF, concentrated HF, we always use PHF, right? So that creates a very, very clean silicon surface, right? Where we get rid of all the silicon dioxide at the end.
And what's the low load of H2O2?
What is what?
The first one, low aluminum hydrogen peroxide.
Yeah, so whatever chemicals we use, they have to be highly pure. No other chemicals should be there. So aluminum is dissolved in those to make them stable. So, but what we have to use has to be very pure.
Also, it's a common impurity in hydrogen peroxide.
So why do you want to have them pure? We don't want other residue to accumulate on the surface of the wafer. Okay, the last line is important. Resultant silicon is stable against oxide load for 30 minutes. What does that mean? Silicon reacts with oxygen even at ambient conditions. What are ambient conditions? Room temperature, right? Normal humidity. And that results into the formation of a very thin silicon dioxide, okay, which is 20 to 50 angstroms, right, depending on humidity and how is the temperature. It may be 25, maybe 35. We don't want that, especially when we are doing oxidation. And we'll see why. I want to touch upon all of these basic processes today as well. What happens during oxidation? When I say oxidation, it's always growth of oxide. When we say growth, what is happening to silicon at the surface? It's getting consumed, right? Now think about it. If I have, what are the requirements for oxidation to occur? Oxygen has to get to a silicon atom, right? But when there is a silicon dioxide layer there, now oxygen has to diffuse through the silicon dioxide layer first, get to the interface, and then react with silicon, right? If I have a wafer with native oxide, it's very thin, but it's still there, 20-25 angstrom, and I have silicon wafer which doesn't have any native oxide. Which one will start oxidizing first? The one with thin layer, the one that doesn't have any layer, right? So in many cases when we want to do oxidation, we want to start with the wafer which doesn't have native oxide. How do we get rid of native oxide?
Apparently BHF.
Dip it in BHF. Right. How do we know what's the thickness of oxide on a wafer? I haven't told you it. I haven't taught you yet. But simple, a very simple way is silicon is glassy, silver. If it has a color to it, there's an oxide. Right? Because that thin oxide film is resulting into light which is not reflecting completely. There's internal refraction with the power. We'll look at what happens. But the color of silicon wafer tells us there is something on top of that. I said something on top of that because it can be a nitride oxide. But generally there is nothing else, and if it shows a color, it means there is an oxide there.
So when we get a wafer from the box, it's going to have an oxide layer?
Normally it doesn't, but it has native oxide always, right? Because after doing that BHF dip or last HF dip, we have about 30 minutes before there is a monolayer of oxide that grows, right? When I say monolayer, means there will be some oxidation start right away, but it's not forming a film completely.
Can we see this happen? Like
Native oxide is too thin.
okay, so we'll never see any.
It's 25 angstrom. There's no direct way of looking at that thin of oxide. But of course, if it is more than that, at hundreds of angstrom, we start seeing the colors.
So ellipsometry or any of those tools won't show us
Depends
that.
with the minimum sensitivity of those equipment. If they can discriminate, their error is above 20 angstrom, they won't be able to give you measurement of 20 angstrom to start.
I see.
Right? So it depends on their sensitivity. Now, again, some common sense. I have two beakers here. They have same wafer. One has, suppose they have same volume of cleaning liquid. Which one is better to use? I have a bigger beaker, a smaller beaker, right? They both are bigger than my wafer, which is lying on the floor. They have same amount
Smaller?
of liquid in there. Which one is better to do?
Say smaller.
Smaller beaker.
The bigger beaker.
The bigger beaker. Why is that? Why is smaller and why bigger?
Smaller because you have less surface area in your chemicals, so you're not going to get stuff from the air in it, and you can have a higher.
Right. So given we haven't isolated the cover completely, yes, that makes sense. We'll have more interface with the ambient. Okay. What if we have them covered, same exactly airtight, so to speak, shouldn't be doing airtight to them because there's always reaction and there are gases coming out and they need to be released. But suppose it's clean room and they're clean, so which one should we use?
Actually, I suppose the larger one has more room for you to manipulate it.
In manipulation, where would you want to use the bigger beaker?
Because it's easier to put in and put out the vapor. Less
Right,
chances
so
of a spill occurring.
It's less chance of spilling it. And now if you think about the volume, if the smaller beaker takes in less volume and I can use more volume in the bigger beaker, which one should I use? So now volume of cleaning solution is less in smaller beaker and more in bigger beaker. What do we use? Have to use your judgment. There's no straight answer for that. So if I have a 4-inch wafer and I'm putting it in a beaker and the cleaning solution is hardly maybe half a centimeter above that, it's going to react and lose its sort of what you call potency maybe in a couple of minutes. It's going to react, say, piranha solution, and soon it will lose its vitality, its reactivity to clean the surface. I may want to use a lot more amount to do that too. So the reaction can continue for about 10 minutes. Sometimes they use heat hot plate as well to keep the solution hot so the reaction continues. Right? So have to use plenty of reactants so the reaction continues for quite a while. This may be straightforward, easy when we are doing maybe SC1 where we don't have any of those chemicals which have fairly low vapor pressure. Right? What is vapor pressure?
The pressure that you measure on a liquid at a given temperature.
So they evaporate, right?
Yes.
So not pressure, evaporating temperature. So they vaporize at room temperature, some of them. So if I use alcohol or acetone, they would vaporize very fast. So we have to, if we want to leave it for 10 minutes, we have to put plenty of acetone so it doesn't dry up during those 10 minutes that you want to leave it. So that depends on what we are doing there. It may not be such a whole 4-inch wafer, it may be a small piece which is a centimeter by centimeter. I may be fine with a smaller beaker for that matter, right? And lesser amount of liquid. It depends on. So remember this HF last. HF last. When we prepare our wafers for oxidation, and we have all that gown on us and protective equipment and very restricted visibility and all that, we sometimes get confused. Should I do PHF first and then piranha and then do oxidation, or should I do piranha first and then PHF and HF last? Always before your last process should be HF. And of course, once you do HF dip, what do we do after that?
De-iris.
You put wafer in HF, PHF. What do we do once we take it out? Rinse it. Right? Put it in DI water. We rinse right away. Put it in a pool of water, and then we put it in running water. Right? Pool of water to stop the reaction immediately all over the wafer. Because when you are rinsing it, you have a tap, and it has a stream which falls at some parts more vigorously than others. So first thing is to take it out and put it into a pool of DI water. It can be another beaker full with DI water, right? Or if we have that cascade, something that we were left at last time, it's called a cascade, where we have these 3 levels of running DI water. The DI water is being filled up at the top cascade, which overflows to the next one, overflows to the next one. So I would take my wafer out of PHF and dip it into the topmost cascade, and then the lower, and then the lower. Right? Right? Right?
No. Lower.
Somebody says no, somebody says yes. Still you guys are not with me. Who said yes? Somebody said yes for sure. I know that. So we put it into the lowest cascade, and then we put it into the middle one, and then we put it in the top one. So we have that water which is flowing. So the lowest one is contaminated and it's flowing out, and the one above it is not yet seeing BHF. Above that, if I start with the top one, then all of them will see BHF, so it loses the idea of cleaning it. So BHF last, and of course BHF leads the washing of BHF as well. That. Right? And we use ozonated water as well, which is we inject it into water. What it does is it's a very reactive species of oxygen. It reacts with resist, right? Most of the resists that we use are organic. So the basic reaction is carbon dioxide formation. So most reactions, that whatever we do with photoresist is basically oxygen reaction, which get rid of all photoresist. Same is the case for D-scum. You guys remember about D-scum? What was D-scum? D-scum process.
Oh, descumming. They're taking the residue off using ozone?
Ozone. Not ozone. We do oxygen. The oxygen clean in a chamber is called descum. You should expect these kind of questions in exams.
Descum is done in all plasma-related processes.
And it's oxygen based, and it's done to do what?
All plasma.
Clean. To clean the chamber, right? So oxygen, there also, most of the byproducts are organic. So oxygen reacts with them and takes them away.
That's FUOL?
Front end of line. And there is difference between front end of line and back end of line processes, right? Why is there difference there? What is the basic difference between PEOL and FEOL processes? Do you guys look at the slides afterwards? I track the views. Blackboard lets me go in and look at who all opened and downloaded those slides. I haven't looked at that yet, but it seems you guys are not looking at those. What is the difference between PEOL and FUOL processes? Discussed this last time. Front end of line, back end of line. When we start with the wafer, it doesn't have too much, right? So we have a larger window of processing. We can put it into any temperature processing. But as we build up, we have some metals, dielectric materials going on there. Our windows are shrinking, both in temperature and what processing we can do, what chemicals we can. So back end of line, front end of line. Back end of line when we start with the bare wafer. Front end of line when we are getting to the front of the wafer. Those processes are not as rigorous as they are for front end of line. Right? So that defines.
So back in the line is when you have metals and such?
Yeah, once you are building up your device, you are putting up dielectric materials, you're putting metals maybe, you're putting a whole bunch of different materials to create your devices. And you have diffusion happen. Diffusion is, and we'll touch upon diffusion. Diffusion is incorporation of impurities, right, to make them electrically active. So diffusion process is a high temperature process. But so more you expose a wafer which has diffusion done, that diffusion will keep on increasing in area because you are heating up. Right? You don't want them to do it. You want the diffusion to stay in that certain region. Going back to that transistor concept, we have the source and drain. These are not physical areas. These are areas defined by the concentration of maybe N-type, which goes on reducing as we go away from those pockets, right? But if I apply more temperature in some next process, this is going to get even further. These are going to diffuse further, right? So your those areas of confined implantation or impurities will not be as confined as you want them to be. So as we go to the front end of line, we are just getting restricted in what processing we can do. And I'm saying we are restricted in what processes we can do, not necessarily just the cleaning. Cleaning is one of the processes. All processes are different for BUL and FUL, right? Look at them later on. So from cleaning point of view, it's also something where we are restricted in how much aggressive reactions we can do on the substrate. Hydrofluoric acid and hydrochloric acid. It's again used as an oxide etch, diluted HF, and ozonated water, which oxidizes everything. Organics, metals, particles. Any questions on cleaning? You guys have to read up on the lab safety, the whole package that was given to you by Nadia. Right? No, it's available on, yes. All of you are certified to work in clean room, right? Have to brush up on those things, what were taught to you in that safety training.
Do we have the first lab available, or will we have
We'll get it, hopefully we'll get you guys today, so you just
So
can
you can
tweak
read
up
it
what to
beforehand.
expect. Right? So let's start with some overview of the processes. Photolithography, we have done this many times. We lay out a design, we have physical representation of device which we transfer onto a plate which is transparent. Now it has some parts which are opaque, right? So the plate have that translation of these device physical ideas into that opaque regions, and masks are multiples. There are many masks which come together, and they are aligned with, they have these certain features in them which are not used in devices, but they are used just to align them, to align one layer of mask with the other one. So we put them on corners for obvious reasons, right? And that region results into the UV not passing through those parts, right? So when we do ultraviolet, right? So remember that we are talking about UV, we are talking about photolithography, or it's called optical lithography. But if we are using some other sources of radiation, it may not be optical, it may be called as something else, deep UV or extreme UV, right? Or then we will not call them photolithography. It might be called E-beam lithography or some other kind of lithography. But when we talk about photolithography or optical lithography, you are talking about the light sources with which we can use optical lenses. Right? What are optical lenses? Where do we see optical lenses?
Right here.
Right? So light can pass through. So a number of wavelengths can pass through. Light is saturation. There are ultraviolets which pass through. There are what do you call it? One is ultraviolet. What is the other side?
Infrared.
Infrared. They can pass through. But if you go on further extremes, many of those wavelengths can not pass through, or maybe they will damage optical lenses. So when we say optical lithography or photolithography, that always tells us what kind of source of light is being used, right? Source of, what kind of source of radiation is being used. Light is again optical. So And accordingly, for this case, when we are using UV, we are using something which we call photosensitive material, right? Optically sensitive material. But if we are out of this optical range, then the coating that we use would not be called photoresist, right? It's called E-beam resist maybe, right? So when you say photoresist, that should also tell you you're talking about an photolithography or optical lithography system. So that material is a liquid, but once we deposit it on a wafer, we spin it, it makes a very thin film, we heat it up, we glassify it. What is glassification process? Glassification process. Where do we see glassification occur?
See it with certain polymers.
So once the solvent evaporates, it leaves a very thin film which cannot be removed unless you use a chemical, right? So the evaporation of solvent results into a hard layer behind, right? So any polymer, when it is heated above certain temperature, and that temperature is called TG, glassification temperature. Once you bring the temperature down, that polymer results into a hard material, turns into a hard material, glass. Before we heat it above TG, it will be still soft. It will be still something that you can squish around and put your fingerprints in there or whatever, just like cement, right? Once it dries off, then it's hard material. So this, what we use, what we call material here, is liquid, but it turns into a solid on the surface, a solid film. And that solid film of photoresist is what we use now to change, chemically change once it is exposed to ultraviolet radiations. So we have seen that before. You have positive resist, and you have a mask, and maybe you have the order right here, and we expose it with UV. That first changes the properties of this chemical here wherever the UV is exposed, right? And then it results into what we can do is development of that resist, which removes only that part but leaves the other parts. And that is what we can use to transfer that design from photoresist into hard silicon dioxide. And then we can do whatever we want to do after that. So looking at this guy and going back to my transistor. Now if I want to just do this implantation of N-type material here, N-type impurity, I can use this window to do that. Right? I can introduce impurity atoms here through this opening, and this will increase in a what do you call, there is a sphere and there is a hemispherical manner. It will be a dome. This is two-dimensional. If you look at it, it's basically I've opened a square in a surface, and now if I expose it to impurities, those impurities are going to grow as a globe. Isotropic is a different concept, but yeah, it will be isotropic, which will be growing into all directions within the substrate. Does it make sense? So it's a dome. Suppose I flip that wafer and my impurity atoms are introduced from the bottom. I have this square opening, but what I get is this maybe a very thin layer of impurity to start with, but as it grows, it results into a dome, right? And that dome grows, and if we can keep on supplying, that dome will grow under that opening as well. Do you understand what I'm saying? You're not seeing my hands. How did you understand what I was saying? Would you know it or not? Do you understand the idea? When you introduce the impurities, 2 dimensional, they will be, so you have a square opening, but once they get in, they will be growing in all directions. So it will be like a dome expanding, right? But the interface of that dome is not a step junction. Step junction is the impurity doesn't just fall off abruptly, right? That interface is where it falls off very fast, but there's a gradual change. So if the substrate is N-type, right, and I introduce a P-type material here, so that's going to expand like this. But this interface is not, if I draw the concentration here, so that concentration is not something that's going to fall like this. It's going to be something more gradual. And well, this is more like, it doesn't go to 0 because there is always some background, what you call, so there is some holes in the N-type material also, what we call minority carriers, right? There's the holes in there. So that concentration falls up gradually in that interface. But conceptually, we can think of it to be a discrete region, right, of that doping. So we do that with lithography. We can, so after it changes chemically by reacting with UV, we put it into a solution where the solubility has changed because of that chemical reaction. The solubility has changed. What is solubility of a material?
Easily dissolves when you dissolve it.
So corrosion, toxicity, carcinogenicity, solubility. That's another quality of every material. Right? So why do things dissolve in a solution? Some don't. So it's an ionization process if they can. So dissolving is basically where the ions, especially for salts, where the ions can separate out. Not all of the things dissolve in all of the solvents. Right? That's the polar and non-polar thing. That if you have a polar solvent, if you have something which can ionize, that will dissolve in it. If it's not, it will not. Right? We know that. So, but I don't want to go there. But just talking about the UV exposure changes that chemical into something that can dissolve into a solution, what we call developer. Right? Once we do that, we remove the exposed part. It could be other way also. It could be just by playing with chemicals. I can have some chemical which, when exposed to photoresist, of course, it undergoes to chemical changes, but that part doesn't get dissolved, and which is not exposed to UV gets dissolved. Right? We can do that. Does it make sense? I mean, define it again. So I can have something. I have slides on that, but the idea of positive photoresist. I have this region which was exposed to UV, right? In photoresist, and that once I dissolve, once I put it in a developer, that region goes away. It could have been that the region which is exposed stays and everything else goes away. Everything else gets dissolved, right? In that case, we will call it negative photoresist. So there's this notion of positive and negative. How do I remember? I remember positive is whatever gets exposed gets cleaned up. I call it positive. Positive attitude. You get exposed, you get cleaned up. Positive attitude. Positive resist. You get clean, you get exposed, and now you become stubborn. Negative resist. Make sense? That's how I remembered it a few years ago. Positive resist gets exposed, walks out, positive attitude. Gets exposed and gets stubbornly stays there, everything gets washed away, it's negative resistance. It can be, okay, so this is about resist only. Now, my mask is also something what we call positive mask and negative mask. Because that we'll get to that later on. We have mask discussion on the mask also. But for now, remember that it's now again the type of resist that is going to be used in the fab now has to be known by the designers of the circuit, because now they will know what kind of resist is being used, so they will put their those physical representation accordingly, right? So now they will know what part needs to be opened up for maybe doping, or what part maybe not. This will sink in more as we get ahead. So, but anyway, unless I tell you it's a negative resist, we'll be always talking about positive resist, right? Fair enough? Unless I specifically tell you we're talking about negative resist, we'll be always talking about positive resist, which will mean wherever UV gets through and reaches the resist, it changes the resist and it gets washed away during color. Now, now think about it. We have now a few factors that we already see which will define the smallest feature we can make. Just like we did that discussion that we can change the thickness of resist by playing with spin speed or by playing with how long we spin it, right? So a thicker resist and thinner resist will give us different smallest dimensions that can be made. Same resist, right? Same mass, but now just because resist is thicker in one case and thinner in the other one, the smallest feature size will be different. Okay, what about smallest feature size? For any process node, for any technology, we know what is the smallest feature size that can be reproducibly made with high yield. Right? So these are important things, reproducibly high yield, and of course we need to maintain throughput also to keep it cost effective. So resist, the light, the wavelength of light that we use, and the mask feature, they all define the critical dimension. And critical dimension is the smallest feature size that can be made. So we'll look at this over and over, CD in the smallest feature size. And there will be certain properties of the whole process that defines CD.
What's more common, positive resist or negative resist?
There's a reason. Negative resist were used in industry, still they are used for some process, but most of those developers and resists are carcinogenic. So they have been phased out.
Really? So the resist we're using is not going to be carcinogenic?
We won't be using negative resist. At least not, we don't seldom use now in research labs, but they are still there. Right? So now CD is the idea which defines the smallest features. Let me give you an example. We are seeing the explosion of LCD TVs, right? So every year they come up with something which has more resolution. What is the current resolution they're selling? They had 760, I think, then they had 1060.
They have 4K now, which is
4K.
like 4,000 something, but it's like a 16 megapixel.
What does that mean? So I look at the screen. What does that tell me about resolution? What does
The distance between two adjacent pixels.
adjacent pixels? So how many pixels can we shrunk? What's the density of the pixel, right? So what defines that?
How far apart they can be.
Okay, what would define how close we can make them? It's liquid crystal display.
Pitch.
It's a crystal material, right? It's something that we fabricate. So it's the CD. of the processing that defines the resolution of your display. How small can we make them? Now pitch is another interesting question. How often can we have them? We can make them small, but we may not be able to have the next guy very close to the first guy. Because resolution is not just the pixel itself, but what can be the distance between two pixels. In one case, we are making a device, but we have also to worry that that device, that one photodiode shouldn't interfere with the next photodiode. Right? Where do we use photodiodes? Where do you use photodiodes?
I mean LEDs or
Photodiodes.
Camera.
Those are light
Sensors.
emitting diodes. What are photodiodes?
those are the sensors, the photo
So,
transistors.
which can look at the light coming into and give it some output. And LEDs are which we can pump in some energy and they can emit light, right? So now they have LED TV. What is LED TV? What is the resolution of LED TV? How small can we make that device on a substrate? All function of CD. Right? So the process node defines how small devices can be made, and that ultimately results into the density of devices that we make on a substrate. Not just how many can we make reliably, how close we can make them to each other, which is pitch, how often we can repeat them. And if you want to really push them down, we use electron or X-rays because they have wavelength of X-rays. Is it above? Is it there? Do they have big wavelength or do they have small wavelength? Small wavelength. So you're pushing to small wavelengths, and we'll see why. If I use X-rays, do I call it optical lithography? What is can optics change properties of X-rays?
Not easily.
Even bones, even flesh cannot change X-rays. They pass through. So the optics don't have any effect on X-rays. So we can't use optical components there. So these are then called EUV lithography, extreme UV. But anyway, this is the sticking to photolithography. If I have this mask and I had this part which was opaque, everything else was transparent. So what got exposed got washed away. What got exposed stubbornly stayed. Negative resist, positive resist. Right? Should now I can using positive photoresist I can still get negative results. If I have my mask designed in a way where I keep this transparent and I have everything else opaque, and I use positive resist, I'm going to get this result, which I would have gotten with negative resist. In that case, I call my mask as negative mask. Does that make sense? Confusing, but have to think it. First, if you know about resist, the one which stays, the one which doesn't stay, and that should tell you that about the mask itself. Now, think about it. If I use negative mask here, what is it better or is it bad? Would it be advantageous or would it not be advantageous? Look at the region that is opaque in this case and consider a region which may be opaque in this case. Which one do I want to use?
Depends on which way you want your slope.
Slope?
Or, doesn't that resist have some sort of a slope?
But we never talked about that. Tell me something common sense. Which I want to use here? Do I want to use something which has much more area which is opaque for me? Or do I want to use a mask which has much more area that is transparent for me? I want to look what's below, right? Especially if I have multiple masks, I want to look through mask and look what is already there on the wafer, right? So we want to have a mask which, if we can, if it's possible, So if you will be designing a mask, and you will be if you work on research project, you have to think what kind of mask you want to design. You want to have much more area to be opaque, much more area to be transparent. Not just for your ease, but for the production of mask as well. You want a mask that has to write much more area. You want a mask that writes. During the mask production, we have to use some maybe E-beam to write those features on the chrome layer, right? So in that step also you want longer writing process or a smaller writing process. So that again, if you want smaller writing process, then you want a negative mask, because the writing basically removes chrome from those parts where you have your design. Make sense? So mask making is then you have a glass sheet which is covered with chrome, and you remove chrome in there to make a part. So now you have to make a trade-off. You want major parts of it to be. Again, another question would be what kind of technology are you using? If that mask is being written with E-beam, yes, it's going to take very long if you have larger area that needs to be transparent. If you are making a mask, again with something like photolithography, doesn't matter. You just have to expose it and etch it into some solution. All right. So what does optical lithography gives us? Repeatable, cheap, and reliable production of those features. Can do very high throughput. Most of the times I'll be talking like we have one wafer and we have a mask which is being exposed and transferring the pattern over the whole wafer. Industry doesn't work like that. We'll see how does industry. Industry basically exposes one part, one die at a time, then the other die, then the other on one wafer. Right? So it's called a step and repeat. Or the machine is called a stepper, which exposes, steps to the next die, exposes, step. So in that case, the alignment has to be done over the whole, from die to die, and keeps on repeating. So it gives you high throughput, gives you high volume manufacturing. Light sources are easy to replace. So, but optical lithography, just get another bulb and it's gonna start doing that. Can you do that with X-ray source? Right? Can we do that same thing for X-ray source or electron beam source? They are much more difficult to replace. Right? So we'll look at the E-beam sources and X-ray sources also. But there is limit of optical lithography, what we call resolution limit. It's a critical dimension, resolution limits. These are all concepts which are very close to each other. So you have to have a clear distinction of what is resolution, what is critical dimension. There will be few more things coming up. Resolution is something which defines the contrast of a feature. Right? Contrast. Can I resolve? I can't resolve those numbers unless I have this glass in front of me. And if I have it, then I can resolve those numbers on that glass. Right? So because they become, I feel there is something, but I can't see the whole contrast completely of those numbers. All the speckies are trying this out. So, and then there are some next generation lithography techniques where we are pushing down on the wavelengths and then using E-beam to directly write those features. So resolution is that size that can be resolved within tolerance. Now, for us, resolution is if we can see the contrast in numbers, but for optical lithography, it's when we make a feature, can we resolve the feature from the rest of the photoresist? So if I expose the light, and I can have something which gives me like this. So this feature, what I wanted was this feature, but I cannot reproducibly get this feature. Or maybe the other way, where I want this feature, but what I'm getting at the top is, so in both ways, this guy is making the resolution difficult. So what I want is not what I get. And there are many things that go into that. Rayleigh criterion, depth of focus, pitch limit. Rayleigh criterion is a simple group of equations which explain the behavior of light once it goes through a slit, right? And we'll see what are those equations that govern that behavior. Depth of focus is, how do you define depth of focus? If I focus my eyesight on one plane, if I look at my hand, everything else is out of focus. So I can't resolve you guys. You guys are out of focus for me. We see that in some pictures where the object is in focus and everything else is out of focus. But if I have higher depth of focus for my lens, I can have everything in focus. That's the concept of depth of focus. The depth of focusing the light rays in Z direction within tolerable limit. Why is that important? It will come up when we look at lithography, but for now, just remember that depth of focus is the allowable focusing of light within certain length in Z direction, in height. And why we're concerned about that, we might have a wafer which has different heights, because we have already maybe made 3 layers of devices, now we are at 4 layer, and we have certain topography of the surface. So when we do lithography, I want that pattern to get transferred over the whole wafer in exactly the same way. But if some part is below, my light will not be in focus at that level, or if it is above, which we know by photography happen. Pitch limit, again, how quickly, how close we can make them. And we'll see why these are important. And there are light sources which use UV, deep UV, and extreme UV, depending on wavelengths. And why their wavelengths is important, we'll look at that. So Rayleigh criterion defines the resolution limit as K1 lambda over Nk. Your Wmin is minimum resolvable feature. Of course, I'll have these slides uploaded. That shows direct relation with lambda. If I want to make my feature size small, which we want to, I want to push the lambda down. And then there is what we call numerical aperture, which is function of the index of medium and the angle at which those lights are converged. So to bring the resolution limit down, either we push lambda down or we push the numerical aperture up. So we are doing, so industry is doing both, but once you look at what you call depth of focus, that is, if I'm exposing my light from top and light is focusing at this plane, right? And I want to have it focused at different levels. My transfer of energy will not be the same to the photoresist. For photoresist to become chemically different, it has to absorb that light, right? And then there goes that chemical change. If my light is not focused at the level of photoresist, my energy transfer will not occur, which means the photoresist will not be exposed completely. It may get exposed partially, but when I do my development, it will not get completely removed, which means I will not be able to get to the active parts of the device. Depth of focus is important. Think about it. Do we want higher value of depth of focus or a smaller value of depth of focus? Now, knowing that depth of focus is the tolerable height in Z in which maximum transfer of energy will occur, because light will get focused completely in that region. If it's defocused, think about it. If light is defocused, what does that mean in terms of energy?
Scattered.
It's scattered. The energy is not getting completely transferred there. It's getting diffused. Right? So I want my image to be in focus, so UV can do what it's supposed to do, change the photoresist chemical. So looking at this wafer and photoresist and looking at different focal planes, what do we want? We want depth of focus to be a higher number or a smaller number?
Higher if you can.
Larger. So we can, whatever topography, we have much more room to just focus it at any plane within that limit and expose it. And we can be comfortable that all the different levels have been exposed at the same level. And once I do my development, they all will result into the features that whatever my mask had. But that has a relation with lambda and numerical aperture. Now, we want to push lambda down to reduce minimum feature size, but that also results into smaller depth of focus. Right? You see that? We wanted to increase numerical aperture to reduce minimum feature size, but now if I do that, my depth of focus reduces by square of that. Right? So it's a competing problem there. And K1, K2 are just constants. So say if I have lambda of 248, I have 270 nanometers of minimum feature size, and I can have only 500 nanometer of room to play in height. So my topographical features cannot be more than 500 nanometers away from each other in height. Does it make sense? This is something I want you to be comfortable with, because this is something which we'll see more and more. So size of pattern at different numerical aperture are defocusing level or depth of focus is going down. Right? So if you push the feature size to smaller size, our depth of focus also goes down, which we have seen by those relations as well. So then for any given numerical aperture, we have to then figure out what is the best trade-off point that we should use. And then is the pitch limit. How often can we repeat? And it's a function of the light parameters. Now think about it. What happens when light enters from one medium to another medium? Glass full of water. What happens to light?
Expands.
Undergoes few things, right? Deflection, diffraction, refraction. What is that? Another one. Deflection. Think about the photoresist as well. It's a thin layer. It's a glassy material, but it has a different index of reflection from the vacuum or air that is there between the lens and resist. So now once light enters the other medium, it's gonna do all those things. And that will result into a feature which is slightly bigger than what we expected. Right? Because in the middle of the feature there's no problem, but the edge of the feature, the light is having internal reflection. So we can end up something which may be bigger than what we have. Now if I have the next guy close by, which is very close, their waves might interfere with each other. So we might not be able to not only maintain minimum feature size, we might not be able to resolve next feature from one feature. When I say resolve, it's the UV change of the photoresist. It may not be able to change photoresist from one spot to the other spot and have certain part in between which is not changed. Say it again. So this guy may be too small for when I do the later process. It may result into one big hole, then two holes. Right? So pitch limit is how often we can repeat them, how closely we can have them, and that's a function again of lambda and numerical aperture. Now here again, if you want to reduce this guy, I don't know what is this guy called, you have to either play with lambda or change the medium so we can have better refractive index. And we'll see what is being done to that. So water can, or oil or some other medium can be used for that. Right? So photolithography you guys will do, but what you will be doing is a very standard procedure, but you want to know what all goes into define the technology node for photolithography. It's wavelength, it's the optics, it's the resist properties, it's the wavelength defines pitch limit, and depth of focus and resolution that we. Any question?